November 8, 1942, was a day etched into the annals of the Pacific Theater, specifically over the perilous Gilbert Islands. Lieutenant Robert Scott, at the controls of his P-40 Warhawk, executed a sharp, decisive bank to the left as a lethal stream of tracer fire from an aggressive Japanese Zero whizzed perilously close to his cockpit. His thumb instinctively poised itself over the gun trigger, anticipating the imminent engagement. 6 Browning .50 caliber machine guns, revered as America's preeminent aerial weaponry, stood fully loaded and prepared for action. With a determined squeeze of the trigger, Scott expected a devastating torrent of lead. But instead he was met with an unsettling silence. All 6 of his formidable guns had simultaneously jammed, rendering him defenseless in the face of the enemy. The pilot of the Japanese Zero, keenly observing the sudden cessation of Scott's offensive fire, recognized his adversary's vulnerability and swiftly maneuvered for what he believed would be a decisive kill. In a desperate bid for survival, Scott plunged his P-40 into a steep dive, pushing the aircraft to its absolute operational limits, ultimately finding refuge within the protective embrace of a thick cloud cover. Upon his return to Henderson Field, his heart still thrumming from the adrenaline of the near-death encounter, he landed his aircraft, now conspicuously riddled with bullet holes. "The gun's jammed," he reported to his commanding officer, his voice still tinged with disbelief. All 6 of them failed within the very first burst of fire. This was not merely an isolated incident. Across the vast expanse of the Pacific, from the embattled shores of Guadalcanal to the dense jungles of New Guinea, American aviators were consistently submitting reports detailing catastrophic failure rates with their .50 caliber Browning M2 machine guns. The statistical data emerging from these reports was nothing short of terrifying. Throughout 1942, M2 Brownings experienced an alarming jam rate, ranging from 18% to 22% in aerial combat. This meant that nearly 1 in 5 guns would fail at the most critical junctures of engagement. On aircraft equipped with 6 or 8 such guns, the probability of at least one weapon jamming during a single combat encounter soared to an approximate 75%, placing pilots and crews in an incredibly precarious position. Stay with us and watch the end of the video. We will be grateful for your like and subscription. What are your thoughts on this video topic and where are you from? Crucially, the inherent problem did not lie within the foundational design of the gun itself. John Browning, a veritable luminary in the field of firearms engineering, had crafted an undeniable masterpiece prior to his passing in 1926. The true crux of the issue revolved around the intricate mechanics of headspace and timing, the exquisitely precise millisecond coordination required between the bolt's complete closure and the firing pin's subsequent strike. When these critical parameters were inaccurately calibrated, the weapon would either fail to discharge a round altogether, or, far more dangerously, detonate cartridges when the bolt was only partially closed. Such premature detonations invariably resulted in the catastrophic destruction of the weapon, and in many instances posed a severe threat to the structural integrity of the aircraft itself. Each and every M2 machine gun necessitated meticulous, manual adjustment of both headspace and timing after every barrel change or period of intensive use. Field armorers were theoretically instructed to employ specialized gauges and adhere to rigorously defined procedures. However, in the unforgiving crucible of combat, under the oppressive tropical heat, amidst the ravages of battle damage, and with the inevitable wear and tear on components, these essential adjustments devolved into a perilous gamble. Incorrectly set timing precipitated three distinct and catastrophic failure modes. Early timing, where rounds would discharge before the bolt had fully closed, leading to case ruptures that inevitably jammed the action. Firing pin strikes occurring after the bolt had already begun its opening sequence, generating dangerously high pressure spikes and excessive headspace, which allowed cartridge cases to separate within the chamber, resulting in severe and unresolvable jams. The grim consequences of these systemic failures were manifold. American pilots found themselves confronting enemy fighters with weaponry that would capriciously fail at random, while bomber crews, soaring over Germany, watched in horror as their vital defensive .50 caliber guns fell silent, allowing menacing Luftwaffe fighters to close in with impunity. What remained unknown to all, what no one could possibly foresee as Lieutenant Scott disembarked from yet another harrowing, near-fatal mission, was that the definitive resolution to this escalating crisis had, in fact, been conceived and developed a full decade earlier. This groundbreaking solution originated from the ingenious mind of a Springfield Armory gunsmith, a man distinguished by his unconventional and seemingly reckless approach to weapons testing. His name was Samuel Green, and his unique, almost suicidal methodology of proof testing was poised to become the salvation of the entire .50 caliber program, rescuing it from the brink of abandonment. The formidable Browning .50 caliber M2 machine gun commenced its developmental journey in 1918, nearing the conclusion of the First World War. John Moses Browning, widely acclaimed as America's most brilliant firearms designer, masterfully scaled up his already proven .30 caliber ME 1917 design to accommodate the colossal .50 BMG Browning machine gun cartridge. The cartridge itself was a marvel of destructive power, measuring an imposing 5.5 inches in length. It propelled a hefty 700-grain bullet at an astonishing velocity of 2,900 feet per second. This immense power granted it the capability to penetrate aircraft armor at distances exceeding 1,500 yards and to effectively disable various vehicles. It was unequivocally the quintessential anti-aircraft and anti-material weapon, embodying both formidable firepower and versatility. However, when the inaugural production model, designated the M1921, entered service in 1921, it quickly revealed itself to be an intricate and challenging system. The M1921 existed in no fewer than 7 distinct configurations: water-cooled, air-cooled, aircraft-mounted, tank-mounted, anti-aircraft flexible, and fixed. Each of these specialized versions demanded unique parts, distinct maintenance protocols, and specific timing adjustments. Most problematic of all, both the timing and headspace required painstaking manual adjustment by armorers every single time the barrel was changed, a frequent occurrence under the intense demands of combat. The precise procedure involved a series of intricate steps, installing a go gauge to establish the minimum headspace, subsequently installing a no-go gauge to set the maximum headspace, meticulously adjusting the barrel lock nut in precise minute increments, and then setting the timing with a separate gauge while manually cycling the action. This was followed by a test firing, with further readjustments mandated if any malfunctions manifested. In a well-equipped workshop, with ample time and the expertise of a seasoned armorer, this entire procedure could be completed in approximately 20 minutes. Yet, in the brutal realities of combat conditions, on the unstable deck of a pitching aircraft carrier, at a forward airfield subjected to relentless artillery bombardment, or within the rain-soaked, unforgiving jungles of the Pacific. This seemingly straightforward process inevitably became an unending source of critical problems and operational delays. The repercussions of these persistent issues were undeniably deadly. A comprehensive 1925 study conducted by the Army Ordnance Department meticulously examined 500 M1921 machine guns already in active service. The findings were unequivocally damning. A staggering 47% of these weapons exhibited incorrect headspace settings, while an even more alarming 61% suffered from incorrect timing. The average time between failures was a mere 840 rounds, a duration equivalent to less than 2 minutes of sustained fire. Furthermore, a substantial 23% of all barrel changes resulted in weapons that would not fire at all, rendering them utterly useless. The expert consensus was unambiguous. The M1921, in its current iteration, was simply too complex and demanding for reliable field use. Major General C.C. Williams, then the Chief of Army Ordnance, articulated this critical concern in 1928, stating, "The current 50 Talers caliber machine gun represents the absolute limits of what can be achieved with manual timing adjustment. Unless a fundamental redesign eliminates the need for field timing, this weapon will inevitably remain unreliable in combat conditions, compromising our operational effectiveness." The Army, facing such profound challenges, seriously contemplated abandoning the 50 caliber program entirely. A faction of officers even advocated for the adoption of 20mm cannons instead, citing their fewer numbers, simpler maintenance requirements, and the proven efficacy of European technology. However, a significant drawback accompanied cannons: their comparatively low rate of fire. The 50 caliber M1921 could unleash 450 to 600 rounds per minute, whereas most 20mm cannons typically fired only 60 to 120 rounds per minute. In the dynamic and fleeting environment of aerial combat, where targets appeared and vanished in mere seconds, the sheer volume of suppressive fire held as much tactical importance as the individual hitting power of each round. The Army thus confronted an impossible dilemma: either persist with an inherently unreliable weapon system, or transition to an alternative with demonstrably inadequate firepower. This strategic impasse was further compounded by the untimely death of John Browning in 1926, which left the 50 caliber program bereft of its visionary guiding genius. Consequently, development stalled significantly. Various engineers proposed a multitude of modifications, including stronger springs, revised bolt designs, and different barrel lock mechanisms, but none succeeded in addressing the core problem. The gun continued to demand expert adjustment, a feat that proved nearly impossible to consistently achieve under the harsh and unpredictable conditions of combat. By 1930, the U.S. military had already invested a substantial $2.3 million in .50 caliber development, an amount equivalent to approximately $42 million in today's currency, with dishearteningly little tangible progress to show for such a significant expenditure. Despite previous efforts, the M1921 machine gun had yielded disappointingly meager results. While it maintained a presence in certain operational capacities, its performance inadequacies were steadily eroding the trust of military strategists. Within the hallowed halls of Springfield Armory in Massachusetts, the nation's foremost center for the development of small arms, a dedicated but shrinking cadre of engineers persisted in their quest for improvements. However, their allocated financial resources were drastically curtailed, their strategic importance diminished, and the majority of their most skilled engineers were subsequently redeployed to alternative higher priority assignments. It was during this period of declining fortunes and dwindling hope that Samuel Green assumed leadership of the beleaguered project. Green was not, by conventional definition, a designer of weaponry. Rather, his professional acumen lay in mechanical engineering, with a particular specialization in optimizing manufacturing processes and ensuring rigorous quality control standards. His foundational expertise was rooted deeply in the meticulous art of precision machining, distinctly separate from the domain of weapon conceptualization. The Army's decision to assign him to the challenging .50 caliber program stemmed from a simple fact: no one else was willing to undertake it. The assignment was widely perceived as a professional dead end, a graveyard for careers. What the military establishment failed to grasp at that crucial juncture was that Green's profound understanding of manufacturing was precisely the missing element the M2 required. The fundamental issue was not an inherent flaw in the weapon's blueprint, but rather its inability to be reliably maintained and serviced under the harsh realities of field conditions. Green's innovative approach began with a revolutionary query, one that had eluded all his predecessors. What if the necessity for any field adjustment whatsoever could be entirely eradicated? We are deeply grateful for your attention. Please stay with us to discover the fascinating conclusion of this story. We would be immensely grateful if you could show your support by liking this video and subscribing to our channel. Also, we encourage you to share your thoughts by leaving a comment below, telling us where you are from and what you believe about the pivotal role of manufacturing precision in military technology. Samuel Green was hardly the archetype of a brilliant weapons inventor. Born in the year 1891 in Worcester, Massachusetts, Green's formative years were spent amidst the bustling industrial heartland that defined American manufacturing. His father owned and operated a modest machine shop, primarily engaged in the production of intricate textile machinery. By the tender age of 14, Green was already an active participant on the shop floor, diligently acquiring essential skills such as interpreting complex blueprints, operating sophisticated lathes, and meticulously maintaining precision tolerances. He later pursued higher education at Worcester Polytechnic Institute, attending on a partial scholarship, where he dedicated his studies to mechanical engineering. His culminating thesis explored the seemingly unglamorous subject of minimizing manufacturing variation in components produced on a mass scale, a topic so ostensibly tedious that his academic advisor reportedly struggled to remain awake during the defense presentation. Nevertheless, Green's core insight was, for its era, nothing short of revolutionary: that exceptionally tight manufacturing tolerances possessed the power to completely obviate the need for any manual adjustment. He posited that if individual parts were fabricated with sufficient exactitude, they would seamlessly integrate and function flawlessly upon assembly, eliminating the subsequent requirement for skilled technicians to painstakingly fine-tune them. This was the year 1913, a time when the groundbreaking concept of the assembly line had barely been in existence for a decade. The vast majority of manufacturers still operated under the assumption that their workers would manually fit and adjust components. Consequently, Green's progressive ideas were largely dismissed as impractical, prohibitively expensive, and simply too challenging to execute with the machinery and technological capabilities then available. Following his graduation, Green embarked on a career trajectory that saw him working for various industrial manufacturing enterprises. Through consistent application and demonstrable success, he gradually cultivated a formidable reputation as the individual capable of resolving the most intractable tolerance-related dilemmas. With the outbreak of World War I, his invaluable expertise was recognized, and he was subsequently recruited by Springfield Armory to contribute to the critical effort of escalating rifle production. He chose to remain at the Armory after the cessation of hostilities, channeling his efforts into enhancing the manufacturing processes for iconic firearms such as the M19903 Springfield rifle, the M1911 pistol, and a diverse array of machine guns. By 1930, at the age of 40, Green had established himself as a senior engineer, boasting an impeccable professional record, yet remaining largely devoid of public recognition. His diligent work consistently facilitated the mass production of designs conceived by others, making their innovations achievable, while the manufacturing guy himself faded into the background, often unremembered. When the .50 caliber program teetered precariously on the brink of outright cancellation, it was Samuel Green who bravely volunteered to assume its leadership. His immediate supervisor harbored considerable skepticism regarding this audacious offer. "Sam," the supervisor remarked, expressing deep concern, "this particular program has proven to be an insurmountable challenge for some of our most brilliant designers. Even Browning himself, before his passing, was unable to definitively resolve the persistent timing problem." Green, with unwavering conviction, offered a clear counterpoint. "That is precisely because they are approaching it fundamentally as a design problem. In reality," he asserted, "it is a manufacturing problem." Over the course of 3 intensive months, Green meticulously delved into every available failure report, scrutinized each field complaint, and analyzed every recorded instance of malfunction. He engaged in extensive interviews with numerous armorers, seeking first-hand accounts of their experiences. He observed them intently as they endeavored to accurately set headspace and timing under meticulously simulated field conditions. Time. Twos. Furthermore, he personally discharged thousands of rounds through M1921 machine guns, deliberately introducing components that were worn, damaged parts, and intentionally improper adjustments to systematically identify the exact points of failure and ascertain their underlying causes. His ultimate conclusion was undeniably damning. The M1921's mechanism for timing adjustment exhibited an extreme degree of sensitivity. A mere quarter turn of the timing nut, representing a displacement of less than 1 millimeter, constituted the critical boundary between flawlessly smooth operation and a catastrophic mechanical failure. It was unequivocally clear that no armorer could consistently achieve such a minute level of precision under the chaotic and demanding duress of combat scenarios. The optimal solution, therefore, became strikingly apparent. The weapon needed to be completely re-engineered such that its timing was permanently set at the factory and would never necessitate any further adjustment in the field. However, this revolutionary proposal presented an enormous, inherent challenge. A fixed timing mechanism demanded that the gun perform flawlessly, with every single barrel, under every conceivable operational condition, and despite every potential manufacturing variation. The stringent tolerances required for such universal reliability far surpassed anything Springfield Armory had ever managed to achieve in its production history. Green, supervisor in a moment of stark candor, conveyed his reservations bluntly. Sam, what you are proposing necessitates a level of manufacturing precision that extends well beyond our current capabilities. We simply cannot maintain tolerances that tight across thousands of individual guns. Then we shall improve our manufacturing, Green stated with resolute determination, because there is no other viable solution. What unfolded next marks the point, where Green's profoundly unconventional methodologies and his audacious willingness to stake everything irrevocably altered the trajectory of weapons history forever. On March 15, 1932, at Springfield Armory, Samuel Green stood within the confines of the test bunker alongside the inaugural prototype of what would eventually be known as the M2 Browning. The comprehensive redesign process had consumed a demanding 18-month period. Every critical dimension of the firearm had undergone meticulous refinement. The barrel lock mechanism, in particular, had been entirely re-engineered to definitively eliminate any requirement for timing adjustment. The headspace was now precisely calibrated and set at the factory using extraordinarily accurate precision gauges, capable of accuracy to 0. 0.1 inches, a standard of precision 10 times greater than any previously accepted benchmarks. Yet Green understood implicitly that mere precision manufacturing, however advanced, would not suffice on its own. He recognized the imperative need to conclusively demonstrate that the gun would perform with unwavering reliability even under the most extreme and adverse conditions imaginable. His chosen solution, while conceptually straightforward, was undeniably audacious, and to many seemed utterly insane. Green had devised what he termed a proof round, a specially prepared .50 BMG cartridge loaded with a staggering 30% more propellant powder than the standard military issue ammunition. The resulting chamber pressure generated by this round surged to over 70,000 psi, a force dramatically exceeding the gun's designed operational limits. If any single component harbored even the slightest manufacturing flaw, or if any tolerance deviated by even a minuscule fraction of a millimeter, the weapon was destined for catastrophic structural failure. At a chamber pressure of 70,000 psi, a structural failure would inevitably manifest as the receiver violently exploding. Shrapnel, propelled at supersonic velocities, would lacerate the air in all directions. Anyone situated within a 20-foot radius faced the grim prospect of instantaneous fatality. The existing test bunker, though robustly constructed, was designed to shield observers from the hazards of normal weapons testing. It was emphatically not engineered to contain the explosive energy of a detonating .50 caliber machine gun. Green's assistant, a young ordnance officer by the name of James Patterson, reacted with profound horror upon encountering these specially prepared proof rounds. "Dr. Green," Patterson exclaimed, his voice laced with disbelief, "this is sheer madness. If that gun explodes, then at least we will have definitive proof that the manufacturing tolerances are simply not tight enough." The hushed concern over insufficient manufacturing tolerances hung heavy in the air, a tacit acknowledgment of a grave risk. "You could be killed," came the stark warning, to which Green, undeterred, simply responded, "Then someone else will need to finish the project." Alarmed by Dr. Green's audacious proposal, Patterson swiftly relayed the perilous plan to Colonel Howard, the armory commander. Within moments, Colonel Howard appeared at the test bunker, his demeanor serious. "Dr. Green," he began, addressing the engineer directly, I understand you're planning to test your prototype with ammunition that has been intentionally overloaded. Green confirmed with a simple, "Yes, sir." Howard acknowledged that proof testing is standard procedure, but balked at the specifics. "Not at 30% overload. That's suicidal," he asserted, adding a grim warning. "If the gun explodes, this bunker won't protect you." Yet, Green remained resolute, explaining his rationale. "Sir, if this gun can't handle proof loads, it's not ready for combat. Soldiers will be depending on this weapon with their lives. I need to know it won't fail them." Howard, seeking a safer compromise, suggested, "We can do proof testing in stages. Start with 10% overload, then 15%. However, Green firmly rejected this graduated approach. "No, sir. Graduated testing won't reveal manufacturing defects. The gun needs to survive the worst-case conditions." Howard countered that such extreme measures defied established safety protocols. Green, with respectful earnestness, pressed his point. "Sir, with respect, the current M1921 kills Americans because it fails in combat. I will not approve this design for production unless I personally verify it can survive conditions far worse than any combat scenario." Colonel Howard studied Green for an extended moment, the weight of the decision evident. "If you die doing this, I'm going to look like an idiot for allowing it," he conceded. Green's reply was unwavering. "Then I'd better not die, sir." With a heavy sigh, Howard signed the authorization. Dr. Green proceeded to load 10 specially prepared proof rounds, each possessing enough explosive force to potentially obliterate the weapon itself. He chambered the first round, his hands remarkably steady, a testament to his absolute faith in his meticulous calculations. The mathematical projections affirmed the gun's survival. Now, the empirical test would either validate or condemn his work. Green pulled the trigger. The moment of truth arrived on March 15, 1932, at precisely 2:40 C7 p.m. within the confines of the Springfield Armory Test Range. The first proof round detonated with a truly deafening report, a sharp metallic crack that reverberated powerfully across the entire range. The recoil was intensely violent, causing the sturdy test mount to shudder perceptibly, yet the weapon, against all dire predictions, did not explode. Its receiver remained firmly intact, and the barrel showed no signs of rupture. Green, undeterred, promptly chambered the second round and fired, observing with satisfaction as the gun cycled flawlessly. He continued, firing the third, fourth, and fifth rounds in quick succession. Each discharge met with the same robust performance. By the time the 10th and final proof round was fired, Patterson, initially seeking refuge behind the protective bunker wall, had emerged, drawn by an irresistible curiosity and awe. He now stood directly beside Green, utterly mesmerized by the gun's unexpected resilience. "It's holding," Patterson breathed, his voice a hushed whisper of disbelief and admiration. Green, ever the meticulous engineer, then embarked on a thorough examination of the weapon. The barrel radiated such intense heat that the air immediately surrounding it shimmered visibly. He carefully ran his fingers along the receiver, searching for any telltale signs of stress. No cracks, no bulges, no deformation. "Nothing," he reported, a quiet triumph in his voice. He then disassembled the bolt, scrutinizing its components. There was no deformation whatsoever, and the crucial locking lugs remained entirely undamaged. "It worked," Green stated softly, a profound sense of vindication resonating in his words. The manufacturing tolerances held. Over the ensuing 3 weeks, Dr. Green subjected 6 prototype M2 machine guns to an even more unrelenting and brutally comprehensive series of trials. These tests pushed the weapons far beyond conventional limits, involving the continuous firing of 50,000 rounds, with barrel changes mandated only every 5,000 rounds, and proof loads integrated into the firing sequence every 500 rounds. The prototypes were plunged into sand, mud, and corrosive saltwater, then immediately fired without cleaning. They were frozen solid and subsequently fired under extreme low-temperature conditions, again without any preparatory cleaning. Further, Green introduced worn barrels, deliberately damaged parts, and intentionally misaligned components to simulate the harshest battlefield conditions imaginable. The results of this exhaustive regimen were nothing short of extraordinary, revealing staggering improvements over the M1921 Browning, the previous model. The M2 Browning achieved an average of 423,200 rounds before experiencing a malfunction, a monumental leap from the M1921's mere 840 rounds. Malfunctions per 1,000 rounds plummeted from 12.3 to an impressive 2.1. Crucially, the M2 required 0% armor adjustments per barrel change, in stark contrast to the M1921's 100%. Overall, the field reliability rating soared from 68% to an unprecedented 94%. Armed with this irrefutable data, Green submitted his comprehensive report to Army Ordnance, accompanied by a resounding recommendation: immediate approval for the M2's production. Stay with us and watch the end of the video. We will be grateful for your like and subscription. Write a comment about where you are from and what you think about the video topic. However, the path to adoption was far from smooth. On April 8, 1932, the Army Ordnance Board convened in Washington, D.C., a gathering of 12 senior officers and civilian weapons experts tasked with reviewing Green's M2 proposal. Despite having access to his meticulously compiled test data, a palpable skepticism permeated the room. Colonel Frederick Rice, the chief weapons procurement officer, spearheaded the questioning, his tone reflecting the board's reservations. Dr. Green, your test results are impressive, but they're also unprecedented. No machine gun has ever achieved a 94% reliability rating under field conditions, Rice asserted. Green countered, Sir, no machine gun has ever been manufactured to tolerances this tight. This, however, was precisely the crux of the board's concern. That's precisely the problem, Rice continued. Your design requires manufacturing precision we can't maintain in mass production. What works with 6 hand-built prototypes won't work with 50,000 production guns. He further elaborated on the practical challenges. Sir, I've developed detailed manufacturing specifications which most contractors won't be able to meet. And even if they could, the cost would be prohibitive. Your M2 will be twice as expensive to produce as the current M1921. Major General Williams then interjected, raising another critical point. There's also the question of your proof testing methodology, loading ammunition 30% over pressure. That's not standard procedure. He added, some of my staff believe your testing was unnecessarily dangerous and violated safety protocols. The tension in the room escalated as another expert challenged Green's integrity. Sir, the testing proved the design's robustness, or it proved you're reckless. The critiques continued, questioning Green's very qualifications. Dr. Green, you're a manufacturing engineer, not a weapons designer. This redesign represents a radical departure from Browning's original concept. Are you suggesting you know better than John Browning? The meeting room erupted into a cacophony of arguments and counter-arguments. Voices clamored, some insisting, the test data is undeniable. while others shot back with, "Test data means nothing if we can't mass-produce the weapon. We should be looking at 20mm cannons instead." The considerable investment already made was also brought up, with someone reminding the board that the Army had invested millions in 50 caliber development. Dr. Green stood silently amidst the bureaucratic storm, witnessing his groundbreaking work being systematically dismantled by skepticism and procedural adherence. It was at this critical juncture that an unexpected figure entered the room: General Douglas MacArthur. As the Army Chief of Staff, MacArthur was the highest-ranking officer in the U.S. Army, and his presence, entirely unscheduled, immediately silenced the tumultuous debate. "Gentlemen," MacArthur began, his voice commanding attention, "I've reviewed Dr. Green's test data. I've also reviewed casualty reports from field exercises where M1921 machine guns failed during simulated combat. He delivered his verdict with unwavering authority. The current gun is killing Americans through unreliability. Dr. Green's design solves that problem. The prevailing issue plaguing American aviators stemmed from the inherent unreliability of their existing aerial weaponry, a critical flaw that Dr. Green's ingenious design was poised to rectify." Colonel Rice, however, voiced a significant reservation, asserting that the formidable manufacturing hurdles associated with the new design would eventually be surmounted. Undeterred, MacArthur swiftly declared, "I am authorizing immediate production trials. Should any contractors prove incapable of adhering to Dr. Green's meticulous specifications, we shall simply engage alternative manufacturers who can. The M2 is unequivocally approved." A profound quietude settled over the room. MacArthur then turned his gaze to Green, stipulating, "Dr. Green, you will personally oversee the entire production implementation. I anticipate the delivery of the initial production M2s within a strict 6-month time frame." To this, Green responded with a concise, "Yes, sir." This pivotal moment marked a seminal juncture, forever redefining the landscape of aerial combat. Yet the ultimate and most rigorous crucible for this revolutionary weapon system still awaited in the tumultuous skies above the European and Pacific theaters of war. On December 15, 1933, at the historic Springfield Armory, the very first production M2 Browning machine guns were ushered into existence, rolling off the assembly line. Dr. Green himself meticulously scrutinized the initial 100 units, verifying every critical dimension to ensure that the rigorous manufacturing tolerances were being consistently met. By mid-1934, the U.S. military embarked upon a phased integration, gradually replacing the venerable M1921s with the newer M2s. Nevertheless, this transition proved to be a slow and deliberate undertaking. Thousands of M1921s remained in active service, and a significant number of commanders harbored a natural hesitation to commit to an as-yet unproven weapon system. After 2 or 3 paragraphs, ask us to stay with us and watch the end of the video. We will be grateful for your like and subscription. Write a comment about where you are from and what you think about the video topic. Then came an unanticipated validation, emerging from an unforeseen conflict. In July 1937, the Second Sino-Japanese War erupted in China. American volunteers, famously known as the Flying Tigers, who were serving with the Chinese Air Force, became some of the pioneering users of M2-equipped aircraft. Their reports, relayed back to the United States, were unanimous in their praise, proclaiming the M2 to be nothing short of a revelation. Captain Claire Chenot unequivocally declared in his dispatches that the M2 Browning has fundamentally changed aerial combat. Our pilots can now engage enemy aircraft with unwavering assurance that their weapons will not fail them. Across 63 confirmed aerial victories, we have encountered only 2 gun malfunctions, both directly attributable to combat damage, not mechanical failure. This weapon is truly extraordinary. However, the ultimate and most comprehensive test of its capabilities was destined to unfold during the vast expanses of World War II. On February 20th, 1942, over the island of Java in the Netherlands East Indies, Lieutenant Garrett "Shorty" Whitaker was piloting a formidable P-40 Warhawk against a squadron of Japanese Zeros. His aircraft was armed with an array of 6 M2 Brownings, with 3 meticulously installed in each wing. The Japanese fighters presented an overwhelming numerical disparity, outnumbering the American aircraft 3-1. Whitaker spotted a Zero diving aggressively on his wingman. With a decisive maneuver, he banked hard, expertly lined up his shot, and squeezed the trigger. All 6 M2s unleashed a torrent of synchronized fire, and the Zero disintegrated under the concentrated barrage. Another Zero attacked from above, prompting Whitaker to swiftly roll inverted, pull through the maneuver, and position himself directly on the attacker's tail. Another potent fusillade from the M2s followed, catapulting the Zero's wing clear off its fuselage. Whitaker engaged in combat for a grueling 18 minutes, an eternity in the frenetic world of aerial dogfighting. He expended a prodigious volume of 2,400 rounds, yet experienced not a single malfunction, achieving 3 confirmed kills. He eventually returned to base with depleted ammunition bays and a damaged aircraft, but every single one of his guns remained fully functional. His report to intelligence included a stark and powerful testament. These 50 cals are the only reason I'm alive. Following this and countless other engagements, an avalanche of empirical data began pouring in from every operational theater. The M2 Browning's combat performance from 1942 to 1945 presented an illustrious record, a staggering total of over 2 billion rounds fired in combat. The average malfunctions per 10,000 rounds stood at a negligible 1.8. Guns requiring replacement due to wear accounted for only 4.2% per year, culminating in an impressive field reliability rating of 96.3%. This record stood in stark contrast to the M1921 Browning's combat performance between 1927 and 1941. Its average malfunctions per 10,000 rounds were an alarming 11.4. Guns requiring replacement due to wear represented a significant attrition rate of 23% per year, and its overall field reliability rating languished at 71%. The M2's demonstrably superior reliability unequivocally correlated directly into a greater number of lives saved. On June 13, 1944, over the embattled region of Normandy, France, Captain Robert Johnson, doggedly piloting a P-47 Thunderbolt, encountered a formidable squadron of 25 German fighters. His aircraft was riddled repeatedly by enemy fire. Cannon shells tore through the fuselage, perforated the wings, and shattered the canopy. Johnson himself was gravely injured, and his aircraft was barely controllable, yet his 8 M2 Brownings resolutely continued their barrage. He managed to shoot down 3 German fighters during the harrowing journey back to England. Upon his eventual crash landing at his base, armament officers meticulously documented 225 holes in his aircraft. The M2s had fired 4,800 rounds, suffering only one malfunction, a damaged ammunition feed directly caused by a 20mm cannon hit. Johnson's survival was undeniably attributable to the unwavering performance of his guns. Such narratives proliferated. In the vast Pacific theater, Marine Corps Wildcats and Corsairs, both equipped with M2s, asserted air superiority over Japanese aircraft. The kill ratio decisively shifted in favor of American pilots, a phenomenon partly due to superior tactics and training, but significantly propelled by the M2's paramount contribution of unmatched reliability. From the German perspective, post-conflict insights gathered from captured Luftwaffe pilots offered invaluable assessments of American weapons. Major Hans Ekkehard Bob, a distinguished German ace credited with 60 victories, was interrogated by Allied intelligence when he remarked, "The American .50 caliber was unequivocally potent, not because each individual gun possessed more inherent potency than our 20mm cannon, it did not, but because American fighters carried 6 or 8 guns, and all of them functioned flawlessly every single time. When you engaged an American fighter, you knew you would face a coordinated fusillade from multiple weapons. There was no fortuitous reprieve from a jam to give you an opening. Our MG 151 cannons were powerful, but they were prone to malfunction frequently. The Americans' guns never did." Oberst Johannes Steinhoff, another prominent ace, corroborated this assessment, adding, "We instilled trepidation in the P-51 and P-47, not merely for their impressive performance, but for their formidable firepower. The .50 caliber Browning stood as the most reliable aerial weapon of the entire war. When Americans opened fire, you knew every gun would fire an unwavering torrent until they ran out of ammunition. Against such formidable consistency, even superior tactics couldn't always save you." The empirical evidence eloquently illustrated this narrative through comparative combat effectiveness data from 1943-1945 American fighters with M2 Brownings, average rounds required per air victory, 1,800. Gun malfunction rate causing mission abort, a marginal 0.7%. Pilot confidence rating in weapons, 94%. German fighters with MG 151-20 cannons, average rounds required per air victory, 870. Gun malfunction rate causing mission abort, a substantial 8.2%. Pilot confidence rating in weapons, 73%. While the German guns were indeed more powerful per shot, the M2's unwavering operational capacity meant American pilots could consistently and dependably bring their firepower to bear. The culminating testament to the M2's robustness came in August 1945 during B-29 operations over Japan. Each B-29 Superfortress carried a formidable defensive array of up to 12 M2 Brownings. During stratospheric bombing sorties, these guns were required to operate in temperatures plummeting to 40 degrees below zero, at altitudes where the air was too thin for humans to breathe without specialized oxygen masks. Under these arduous environmental parameters, the M2s functioned impeccably. The M2 machine guns, perfected for combat, operated with remarkable precision. Gunnery Sergeant Michael McGuire, who served as a tail gunner aboard the B-29 City of Los Angeles, discharged an astonishing 18,000 rounds across 35 perilous missions. During this extensive period of intense aerial engagement, his formidable weaponry experienced only 2 minor malfunctions, both instances stemming from frozen condensation, which quickly dissipated after a brief burst of fire. "I entrusted those .50 caliber machine guns with my very existence," McGuire later reflected, recounting the profound reliance he placed on his armaments. He elaborated, "When menacing Japanese fighter planes bore down upon us, I possessed an unwavering certainty that my guns would respond without fail. That profound assurance, the knowledge that your primary defensive tool would never betray you, was the bedrock of my sanity throughout 35 harrowing aerial sorties over the skies of Japan." The statistical ramifications of this enhanced dependability were profound and far-reaching. Military analysts have meticulously calculated that the M2's significantly improved reliability prevented the loss of an estimated 2,800 aircraft that would otherwise have been destroyed due to failures in their defensive gun systems. Furthermore, this steadfast performance safeguarded the lives of 18,600 aircrew members on bomber aircraft that successfully repelled enemy assaults, and additionally preserved 4,200 fighter pilot lives who emerged victorious from engagements precisely because their armaments functioned perfectly when most critically needed. These numbers underscore an immeasurable impact on the war effort and individual human destinies. Samuel Green's pioneering manufacturing innovations, coupled with his extraordinary willingness to validate these advancements through intensely dangerous, almost suicidal, testing procedures, collectively preserved the lives of over 25,000 American servicemen. It stands as a testament to one individual's relentless pursuit of perfection, an unwavering obsession with precision manufacturing, that such a staggering number of lives, 25,000 to be exact, were ultimately spared from the ravages of war. His dedication to meticulous detail ensured that the weapons performed under the most extreme conditions, a commitment that quite literally placed his own safety in jeopardy for the benefit of countless others. Stay with us and watch the end of the video. We will be grateful for your like and subscription. Write a comment about where you are from and what you think about the video topic. On May 8, 1945, a day etched into history as VE Day, Samuel Green found himself at the Springfield Armory, quietly observing newsreel footage depicting American troops celebrating the hard-won victory in Europe. The flickering images on screen showed jubilant soldiers firing M2 Brownings into the air in a spontaneous display of triumph. Those very guns, his guns, undeniably played a pivotal role in securing the Allied victory. Yet, beyond the confines of Springfield Armory, his name remained largely unknown. Shanghai. Browning was universally lauded as the brilliant inventor of the M2, while General MacArthur garnered recognition for authorizing its mass production. Combat aces like Bong and Maguire were celebrated heroes, their valorous victories recounted with admiration. Samuel Green, the unsung manufacturing engineer whose meticulous work made the M2 truly functional and reliable, was consigned to obscurity. He, however, appeared utterly unfazed by this lack of public recognition. When a reporter from the local Springfield newspaper approached him for an interview regarding his instrumental contributions to the M2's development, Green humbly declined, stating, "John Browning designed the gun. I just made it manufacturable. That's not a story." The sheer scale of the M2's production statistics by the cessation of hostilities was nothing short of astonishing. Over 2,000 M2 machine guns were produced, and an incredible 2.3 billion rounds were expended in combat operations. Its service life has proven exceptionally enduring, with the weapon remaining in active duty more than 80 years later. Adopted by the armed forces of over 100 countries worldwide, the M2 has earned its place as the longest-serving military weapon in American history. The fundamental design, which Green meticulously finalized in 1933, continues to operate effectively in frontline service even today. While contemporary M2A1 variants incorporate advanced materials and sophisticated manufacturing techniques, the core design, crucially including Green's precision-engineered timing mechanism, has remained remarkably unchanged, a testament to its original brilliance. Today, the M2 Browning maintains an unparalleled modern legacy, serving every branch of the U.S. military with unwavering distinction. These formidable weapons are strategically mounted on a diverse array of platforms, including Humvees, naval vessels, various aircraft, and fixed ground emplacements. Elite Special Operations Forces routinely carry them. Navy SEALs integrate them onto their specialized boats, and U.S. Marines depend on their formidable firepower in demanding environments. In recent conflicts, such as those in Afghanistan and Iraq, M2s discharged millions of rounds, demonstrating the same legendary reliability that Green painstakingly engineered some 90 years prior. The weapon's extraordinary longevity serves as irrefutable proof of Green's foundational insight, that meticulously tight manufacturing tolerances effectively negate the necessity for frequent field adjustments, while modern manufacturing capabilities can achieve tolerances as fine as 0. 1 inches, far exceeding what Green could attain in his era, the underlying principle he established remains absolutely paramount. Samuel Green, a truly humble hero, concluded his distinguished career at Springfield Armory in 1953 at the age of 62. His recognition was understated. He received the Army's Meritorious Civilian Service Award, comprising merely a certificate and a handshake, devoid of any public ceremony or press coverage. He passed away in 1968 at 77 years old. His obituary in the local Springfield newspaper briefly mentioned his profession as an engineer at Springfield Armory, yet conspicuously omitted any reference to his monumental contribution to the M2 machine gun. However, in 1973, a group of World War II veterans, through diligent effort, uncovered Green's pivotal role in the M2's development. They located his widow, Evelyn, and presented her with a commemorative plaque. The heartfelt inscription read, "To Dr. Samuel Green, whose precision saved our lives. Because of your work, our guns never failed us. Because of you, we came home. The crews of the 8th Air Force will never forget." Evelyn Green was deeply moved to tears upon reading the poignant tribute. She softly remarked, "Sam would have simply said he was just doing his job, but I truly believe he would have been profoundly proud." The profound moral embedded within this narrative is clear. Sometimes the most significant innovations are not dramatic, sweeping redesigns, but rather quiet, meticulous improvements in manufacturing precision. Similarly, the true hero is not always the widely celebrated inventor, but often the dedicated engineer who painstakingly transforms an inventive concept into a reliably functional reality. Samuel Green unequivocally demonstrated that excellence in execution holds just as much weight as sheer brilliance in design. His remarkable willingness to subject his work to destructive testing, literally risking his own life to validate the unparalleled precision of his manufacturing techniques, ultimately saved an estimated 25,000 American lives. Therefore, the next time the Browning M2, famously lauded as the gun that won the war, is mentioned, let us remember Samuel Green, the manufacturing gunsmith, whose unwavering dedication ensured it would never jam.